In this section, we look at acid-base titrations. The main purpose of an acid-base titration is to determine the concentration of an unknown acid or base by a neutralization reaction using a solution of known concentration. In order to determine the concentration of the unknown, we have to determine the equivalence point of the titration. And this is the point in the reaction in which the number of moles of strong base added, OH-, equals the number of moles of H0+ that was originally present in our sample, or vice versa. However, the problem is that it is not experimentally possible to determine the equivalence point. And so what we do is we determine the endpoint of the titration. And this is the point in the reaction when we observe a visible color change. And we do this using an indicator. The indicator should be selected so that the color change of the indicator coincides at or very close to the pH of the equivalence point. And so the visible endpoint or color change from the endpoint signals the invisible equivalence point in our titration. Here we have an example of a titration setup where we have our unknown solution in an Erlenmeyer flask and our titrant in our burette. And in this experiment, we add our titrant to our unknown sample gradually, and we wait until we see a color change. In this example here, we see that not enough titrant has been added. And on the example on the right, we see that we have too much titrant added because the color change is too dark. However, in the middle here, we've added just enough titrant to match the endpoint. And at this point, the moles of hydroxide that are added equals the number of moles of H0+ that were originally present in our sample. In this example, we have the titration of a strong acid, which is our sample, with a strong base, which is our titrant. And here we see the experimental setup, where we have our sample, which is contained in an Erlenmeyer flask. In this case, it's HCl, or hydrochloric acid, which is a strong acid. And we have our titrant, which is placed in a burette, which in this case is sodium hydroxide, which is a strong base. Here we have an example of a titration curve for a strong acid, strong base reaction. And we can see here that at the beginning of our titration, before we've added any strong base, so before we've added any hydroxide, we only have our strong acid present. And so this strong acid will undergo a strong acid reaction and dissociate completely, producing H0+. And so as a consequence, at the beginning of the titration, the pH starts off very low. Later in the titration, when we begin to add our titrants, which in this case is hydroxide, to our sample, we see that the hydroxide from our titrant reacts with the H0+ from the sample in a neutralization reaction. And in that process, it produces water. And we can see that here. So initially, we start with a large concentration of H0+, and we add a small concentration of hydroxide. And that hydroxide reacts completely with the H0+ to produce water. As the titration progresses, we continue to add our titrant or hydroxide to our sample until we reach the equivalence point, which is located here in the titration curve. As you may recall, at the equivalence point, the number of moles of hydroxide added equals the number of moles of H0+ that we start with. And we can see that here in this reaction. So we have exactly the same reaction as we saw on the previous slide, but in this case, we start with the same number of moles of H0+ and OH-. Now, this will proceed as a neutralization reaction, and so all of the OH- that we add will react with all of the H0+ that was originally present in our sample, producing water. So in other words, all of our H0+ and all of our OH- are converted to water. And since the pH of pure water is 7, the pH at our equivalence point is pH 7, as we see here. After we pass the equivalence point, we continue to add our titrant, which is hydroxide, to our unknown sample. And after we've passed the equivalence point, we have an excess of hydroxide. And so at this point, all of the H0+ in our sample reacts with some of the hydroxide that we've added to produce water, But at this point, we have an excess of hydroxide remaining in our sample. And it's this excess hydroxide that determines the pH of the sample after the equivalence point. Here we show the titration curves for strong acid, strong base titrations at 3 different concentrations. You can see that regardless of the concentration, the titration curves take the same basic shape, and the equivalence point for all 3 titrations is pH 7. However, the effect of the concentration we see is that as the concentration decreases, the starting pH of the titration increases, since pH is determined by the concentration of the acid. In addition, we see that the curves become shallower, or, as we see in this text, the steep part of the curve becomes shorter as the concentration of the acid decreases. Finally, once we pass the equivalence point, we see that we will have an excess of our strong base, hydroxide. And at this point, all of our weak acid will react with some of hydroxide to produce the conjugate base A-. And here, we will have a mixture of our strong base OH- and our weak base A-. And most of the time, the pH of this mixture will be determined by the concentration of the strong base OH-, since our strong base will have much more of an effect than the weak base.